Today's topic is op-amp comparators. As the name suggests, it is used to compare two voltages. Okay, used to compare two voltage levels. Okay, so what it means, comparison of two voltage. If we have two voltages, let it be V1 and V2, we want some device to check whether if V1 is greater than V2, then it should be an output, or if V1 is less than V2, it should be a 0. Okay, it is logic high, and this is logic low. Okay, a device which can check whether if they given in voltages or how they are different. Okay, different, how they are whether they are high or low compared with each other. Okay, so if one is higher than the other, we should either want a logic high or logic low. Depending upon the output, we can either make it an logic high or logic low. Okay, by using NOR operation. Okay, NOT operation. So we can use op-amp as an comparator. The circuit is very simple. It's an open loop configuration. If you remember, the open loop configuration is given by this circuit. Okay, here we give the two voltages V1 and V2, and here we have the output. There is no feedback. Okay, this configuration is called open loop configuration. In open loop configuration, we know that the output voltage is open loop gain times the difference between the V1 minus V2, difference between the input voltages. Okay, because this is negative, our V2 should be negative here. Okay, in the output. So usually our open loop gain is of order of 10 power 6. Okay, so if the difference is even though the difference is very minute, the output voltage is very high. Okay, usually if the output voltage is greater than or of the order of our biasing voltage, then usually what happens is the output voltage saturates either to the plus VCC or minus VC depending upon the input signals. Okay, so in this case, if V1 is greater than V2, then our V0 is equal to plus VCC. Okay, it's what it means is if V1 is greater than V2, then it saturates to the upper saturation. Okay, if V2 is greater than V1, then it saturates to the lower saturation voltage. Okay, so if V1 is less than V2, then in this case it saturates to minus VCC. Okay, because no here, okay, I took V1 as the positive input. Okay, if V1 is less than V2, then it saturates to minus VCC. Okay, this voltage, nearest voltage. Okay, in this way we can compare the two voltage levels. Okay, so the configuration is an open loop configuration. That's the idea. Okay, so what happens if we do this thing to the circuit? So instead of connecting the bias to plus VCC and minus VCC, what I am doing, I am giving plus VCC, and instead of connecting the negative voltage, I am grounding that pin. Okay, so this is our output, this is plus, this is minus. Okay, so we have V1 and V2. So in this case, if grounded means, if V1 is greater than V2, that is, this one is high, so it saturates to the higher voltage, therefore Vout will be plus VCC. Okay, and if V2 is greater than V1 means it saturates to the lower voltage, therefore our output will be 0 volts. Okay, so this is logic high, and this is logic low. Okay, in this way we can, instead of going to the negative region, we can make it 0. Okay, by tying the pin number 4 to the ground. This is pin number 7. So usually, instead of having two voltages as V1 and V2, what we do is we make one of the voltages the reference voltage, and we compare the other voltage with reference to this one. Okay, so usually the reference voltage can be in the inverting terminal or the non-inverting terminal. Okay, based on that the output also changes. Okay, so let's see how we can make a non-inverting comparator. So instead of V1 and V2, we can have a reference voltage in the inverting terminal, therefore this is called V reference. Okay, we are going to compare this voltage, V input voltage, with reference to this voltage. Okay. So this is in a non-inverting configuration. Okay, non-inverting in the sense the reference is given to the inverting terminal, therefore the input is given to the non-inverting terminal. Okay, so this is determined by where the input goes. Okay, so if the input goes to the non-inverting terminal, then the comparator is called a non-inverting comparator. If the input goes to the inverting terminal, then the comparator is called inverting comparator. Okay, so let's see how this voltages behaves in a graph. Okay, let me put it in a new page. Therefore, so let's our input be a triangle wave. Okay, so this is our reference voltage. Let me draw in another color. So this is our reference voltage. Okay, V reference, and let our input voltage be a triangle wave. So this is our input voltage V, okay, in triangular form. Okay, so we know that whenever the input voltage is greater than V reference, we have a logic high. Okay, logic high. If our input voltage is less than V reference, we have a logic low. Okay, logic high means 5 volts, logic low is 0 volts. Okay, that's the difference. So let's see how the output looks like. So this is the time axis. So here also the time axis is the time axis. So if we look till this part, our input voltage is less than the reference voltage, therefore it will be a logic low. Okay, so from here onwards it will be logic high. Let me draw in a line. So our output looks something here. In this part, our input is less than the reference voltage, therefore according to this condition it will be low. Okay, here it will be low. Okay, here the input voltage is greater than our reference voltage, therefore it will be high. Okay, logic high. And at this point the input voltage again becomes lower than our reference voltage. So in this region, full region, it will be low, and here it is again higher than our reference voltage, therefore it will be high. Okay, so in this way we have changed our triangle wave into a square wave. Okay, so this is also a kind of wave shaping circuit. Okay, usually comparators are used to compare voltage, or they are also used to shape as a wave shaping circuits. Okay, so this is how the non-inverting comparators look. Okay, the output voltage of the non-inverting, this is V out. Okay, so let's see how the output of an inverting comparator look like. Okay, so it is the inverse. Okay, whenever the voltage, let me draw it again. Okay, so this is inverting comparator. So since this is an inverting comparator, the input is in the inverting terminal. Therefore, obviously the reference goes to the non-inverting terminal. Therefore, this is Vref. Okay, here we have the V input, and here we have the output. Okay, and this is plus VCC, and this is ground. It should be grounded. Okay, in both cases it should be grounded. Here also it should goes to plus VCC, and this should be grounded. Okay, then only it will go to 0 level. Okay, this level. Here in this case the situation is reverse of that of the non-inverting case. So whenever if V in, okay, greater than Vref, if it is greater than Vref, V in greater than Vf, it will goes to 0. Okay, V out equal to low. Okay, logic low. If V in less than Vref, V out is high. Okay, logic high. Okay, if whichever thing is greater, it will saturate to that point. Okay, that. So here it is inverse. Okay, if you look that V in is greater than Vf, and it is logic high, whereas here if V in is greater than Vref, it is logic low. Okay, because the input, because it's an inverting comparator. Therefore, let's look how the output looks like. Okay, so this is time, this is our logical output waveform. Let it be in blue color. Okay, so this is input voltage V in. It can be any waveform, but it is easier to explain through triangular way. I am using this waveform. Okay, so our V reference is somewhere here. Let it be somewhere here. Okay, so how our output looks like. This is time, this is the voltage. So whenever our input voltage, this is our input voltage, whenever the input voltage is less than V reference, it is high. Okay, in whenever V in is greater than V reference, it is low. Okay, so let's draw the partition lines. So our output looks like whenever V in is less than V reference, it's logic high. Okay, so it's an inverted case. So it's a logic high. Whenever V in is greater than V ref, it's logic low. Okay, and here it is logic high, and here it is logic low. Here it is logic high. Okay, so this is the output. This is V out. Okay, so our output looks like for the inverting comparator. Okay, it is an inverted waveform, therefore it is called an inverting comparator. Next thing is what we are going to see is called window comparator. Okay, the next thing is window comparator. So what we see earlier, we have a single reference voltage, and if depending on the type of comparator, if the input is less than the reference voltage, it shows some sort of logic. Okay, but here we have two levels. Okay, low level and high level. Whenever the input voltage is in between these two levels, then depending upon the comparator, we may have logic high or logic low. Okay, such kind of comparators is called window comparators, because we are comparing between two values, low and high values. Okay, such comparator can be constructed using inverting comparator and non-inverting comparator in the following configuration. Okay, the first top one is an inverting comparator. So, it's an inverting comparator. Therefore, its input should go to this terminal, right? And the second comparator is a non-inverting comparator. Okay, therefore the input should go to this terminal. Okay, so these two terminals are tied together, and the input is given to this common pins. Okay, and this pin, okay, this pin of the, this is an inverting, okay, inverting op-amp, this is non-inverting op-amp or comparator, right? So this is the high voltage reference. Okay, it's a reference voltage, so let me write it as V ref of H. Okay, high voltage, and here it's V ref of low voltage. Okay. And we have to give plus VCC to both the ICs, VCC, okay, to pin 7, and pin 4 is tied to ground. Okay, pin 4 is tied to ground. Also, we have to put the output of these two comparators through a AND gate. Okay, so here is what we get the output. Okay, so let it be the comparator A. Okay, let it be comparator A. Let it be comparator B. Okay. So we have VA and VB. So we know that from the truth table of AND gate, we will have the output only when VA and VB both are high. So since this is a non-inverting comparator, so this is an inverting comparator, let me mark it. This is inverting. Okay. And the second one, let me see. Second one is non-inverting configuration. Okay, non-inverting. So let me draw the outputs for all the cases. So let's try for the first inverting case. Okay, if Vi, the input voltage, is less than our Vh, okay, V ref of H, then we have Va equals to what we have when V ref is less than Vi, that means V ref is greater. Therefore, it ties the output to the upper saturation voltage. Therefore, we have a logic high, right? Okay, instead of logic high, let me write it as 1. Okay, and if Vi is greater than V ref of H, okay, upper reference voltage, and Vi is greater than Vref, then it will tie to the lower saturation voltage. Therefore our Va equal to 0. Okay, since it is grounded, it ties the output to the lower saturation voltage. Similarly, we have to examine for the non-inverting case. Okay, so if Vi is less than Vref of low, okay, this one, okay, low, then we have Vb equals to, then our input voltage Vb equals to, what is the case if Vi is less than Vref? So whichever thing is larger, okay, wherever the larger sign is, it will tie that to that pin. Okay, the output will be tied to that pin. Okay, then if Vi is less than Vref, then Vb equal to ground. Okay, therefore we have a logic 0, and if Vi is greater than Vref of low, then since the greater sign is on the Vi side, okay, Vi side, it will tie the pin to the positive saturation voltage. Okay, then therefore we have the output as logic 1. Okay, okay. So, so depending upon the value of Vi and Vi with reference to V ref of H and Vi with reference to V low of H, we have four combinations. Okay, for the inputs of this AND gate. Therefore, the V out varies depending upon this AND gate. Okay, let's examine that point. Okay, so the next thing we have to check is if 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 the input is the moment before the input is switched on, both V ref of L and V ref of H are greater than the input voltage. Okay, when the input is given, when that the moment of input, okay, at that moment Vi is less than both V ref of L and Vi is less than V ref of H. Okay, so in this case, let's examine what is Vb and Va. Okay, so if Vi is less than V ref of L, this case, okay, then Vb equals to 0, and if Vi is less than Vref of L, Vi is less than Vref of L H, Vref of H, we have Va equal to 1, right? Since Va and Vb are not identical, we have V out equal to 0, right? Okay, let's examine what's the case for, let me use black color. Okay. If Vi uh, is greater than the lower threshold Vref of L, but if Vi is less than Vref of H, okay, we can see all these things in a time waveform diagram shortly. Before that, let's examine this. Okay, therefore our Vb equals to what? If Vi is greater than Vref of L, Vi is greater than Vref of L, sorry, Vref of L. Okay, we have Vb equal to 1. Vb equal to 1. Similarly, if Vi is less than Vref of H, okay, in this case, we have Va equal to 1. Since this both inputs are high, the AND gate shows an logic high, right? Okay. So what if Vi is now greater than both the reference voltage L and Vi greater than Vref of H. Okay. So in this case, we have Vb equals to 1, okay, whereas Va goes to 0. Okay, if you look at this table, okay, Va equals to 0, right? Therefore, our output equals to 0. Okay. So we have another possibility. If Vi um, less than Vref of L and Vi Vi greater than Vref of H. Okay. So if we examine this is not an possibility, because if Vi is less than V reference, if it is lower than the lower threshold, it can't be greater than the higher threshold. Okay, so this is not possible. Okay, even though we can analyze its output. Okay, because we have the uh, uh, reference table for all this one. Okay, so what if um, so Vb equal to 0 and Va also equal to 0. In this case, Vb equal to 0, also Va equal to 0. Therefore, the output equals to 0. Okay. So let's see all these things in a neat wave diagram. Okay. So let me go to next page. Okay. So let's see what happened. Uh, high is gray and low is green. Okay. Let our input be a triangular form. Okay, it can be any form, but let's assume it to be a triangular form. And this logic holds for any kind of waveform. Okay, so our low point is green color. So this is our low voltage, low threshold level, and we have a high threshold level. This is our high threshold. So this is V ref of L. Okay, and this point is V ref of H. Okay, so this is the higher threshold level. Okay. And this is the time axis. So let's examine each part and see how it the output behaves. Okay, so this is also time axis. This is the V out. Okay, so let's draw parallel lines. So this point is when this point is V in is less than V reference. Okay, this region. Okay, in this region, V input. Okay, the input voltage. This input voltage. This input voltage is less than both the lower and upper threshold references. Okay, in this region. Okay, so the output looks like, so when both the logics are zero, let me have, when both we input both when the input is less than both the lower and upper threshold, we have the output as zero. Okay, so it is logic zero. Therefore, here we having a zero voltage. Okay, so it will be zero. So in this region, okay, it is greater than, okay, this region. Okay, the input voltage is greater than the lower threshold, but it is less than the upper threshold. Okay, so Vi here, here Vi is less than VL and Vi is less than VH. Okay, here, okay, Vi is less than VH, but it is greater than VL. Okay, in this region. Vi greater than VL and Vi less than VH. in this region. So it is logic high. Okay, and it should be logic high because it's a window comparator. Whenever our input voltage is in between the lowest threshold and highest threshold, we should have a logic high. Okay, so what if our input voltage is greater than both the lower and higher threshold? Here it is greater than V reference of L and V reference of H. Okay, here to here in this region. And if it is higher than both the lower and higher upper threshold, it should be logic low. Okay, so it is logic low. And if it is, again it comes to our window region, therefore it should be high. Okay, should be high, logic high. And here and here. Okay. Here it is in this region. It is the input voltage is less than our both VH and VL. Therefore, it is logic low. Okay, it's logic low, and here also it is less than this case. Okay, it's logic low. Therefore, our output looks something like, okay, this. Whenever our input voltage Whenever our input voltage is in between this region, it will have an logic high. Okay, or else it will have a logic low. So this is called a window comparator. Okay, with this the comparator is the discussion about comparators using op-amp is over. In the next, we will see how to use this comparator to make oscillator circuit. Okay, so it is about the triple five timer oscillator. The next discussion is about triple five timer oscillator. Okay, thank you.